All right, today we're continuing our review for the final exam in Chem 100. And we left off at number 71. That's where we're going to pick it up. This review document, like I said before, is in bright space. There is also a key to go with it. And let's see. Yes. And there's a worked problems document that I've made for this one, as well as all the previous exams. You'll recognize that this document is in my handwriting, and it works the problems that we actually every problem in the review document for the final exam is worked out here. So you'll be able to find any one that I've highlighted and we've covered in class. All right, number 71. Convert 0.205 moles of calcium hydroxide into so many grams of calcium hydroxide. This is what we call dimensional analysis problem. It's a unit conversion. 0.205 mole of calcium hydroxide. First of all, is that written correctly? Well, calcium is an alkaline earth, so it should be a 2+ charge. And hydroxyl is a polyatomic ion that you can find in useful information in any of the tests, and will be available for you to use during the final exam. It'll be in the same folder where you'll find the final exam. Useful information. It's a -1 chart, so 2 times -1 cancels 2+. So we're good there. Now let's answer the question. What do we need to do to convert this to grams? Moles is in the numerator, so the conversion factor puts moles in the denominator. Grams is our target. It has to be in the numerator. So that tells you that grams and moles as a quotient is molar mass. We need to find the molar mass of calcium hydroxide. So we look at our periodic table and we find that calcium is about 40.08 grams per mole. We have 2 oxygens, 16 grams each, and we have 2 hydrogens, 1.01 each. So we just add those up. And I get 74.10 grams per mole. Okay, this is grams per mole, and that's what we need. We need grams on top. Like that. That way, moles will cancel and leave us with grams. So, like I always say, that's the thinking part. The rest is number crunching. So, and you still have to know how to crunch your numbers, right? Learn how to use your calculator. 0.205 and times, let's see, 74.10, which is, my calculator tells me 15.1905. This is a conversion factor. Remember our significant figures rules. Conversion factors are exact numbers. They don't influence the outcome at all. This one has three significant figures, right? That zero doesn't count. This zero does count. 1, 2, 3. So we can have 3 in our answer. So we have 3 significant figures rounded to that position. Right? Immediately to the right is greater than 5. So this one is rounded up to 2. So your answer is 15.2 grams. All right. Moving along. I think this board needs some work. Pardon me for just a minute. Here we go. Yeah, let's see if that works better. Next, let me just skip a few conversion factor problems, and then we come to 78. When 10 moles of calcium metal is reacted with 3.9 moles of oxygen gas, how much calcium oxide is produced? All right, this problem tells you what the reactants are and what the product is. Calcium metal. That's a solid. Oxygen gas. This is where you have to remember the diatomic elements. It just says oxygen gas. If you write O, then you can't balance the equation. You have to have O2. Yields calcium oxide. So let's write calcium oxide correctly. Calcium and oxygen together. Is that balanced? Remember, calcium is an alkaline earth. Oxygen is a chalcogen. So yeah, just one of each is all you need. Now, I said it wouldn't balance. Now, it could balance incorrectly. If you only had one oxygen here, then you'd say that one plus that one equals that one, and you'd be wrong. Right? Then you would not be able to solve the problem. But this way, we have to balance the equation. We have 2 oxygens here. We need 2 here. Now we've got 2 calcium. There's your balanced equation. Now we can go to solve the problem. 10 moles of calcium metal reacted with 3.9 moles of oxygen gas. Okay. In order to determine how much of this is produced, we have to know which one of these is limiting. Whenever you've got a reaction and definite amounts of the reactants are given, you can be pretty sure that one of them is going to run out. One of them will be limiting. So we have to determine which one is limiting. There are a couple of ways to do this. One way is to say, all right, if all of that calcium is used, in other words, if this is limiting, then how much of this does it produce? Well, 10 moles, since the ratio is 2 to 2, then 10 moles of this will produce 10 moles of product. And then if we say oxygen is limiting and all of it is converted, if all of this is converted, the ratio is 1 of these to 2 of those. So one way to do that is just to say, if this is O2, then what's the ratio? O2 on the bottom, calcium oxide on the top. We have 2 here and 1 there. That means 2 times that. So 7.8 moles will be produced. Then you compare. The one that produces the least amount is the limiting one. That means this is limiting. And calcium is excess. Now that's the sure way to do it every time. And if you're looking for a product, then this is a good way to do it, because once you find the limiting one, you've already got the answer. But you can also say, all right, if this 10 moles represents 2 calcium and 3.9 moles represents 1 oxygen, then you can compare the coefficients here, right? If this is 2, then how much oxygen is required? To use up all of this, you would need half of that. Right? But you don't have half of that. You've only got 3.9. That means you don't have enough oxygen. That makes oxygen limiting. And then you can proceed to calculate calcium oxide. Those are 2 different ways to solve the same problem. But the answer is 7.8 moles, D. All right. 81 and 82, we'll get them both on there. 81. For the reaction, 2 sulfur, there should be a plus sign in there. 2 sulfur plus 3 oxygen yields what? 2 sulfur trioxide, which should be a gas. Okay. Now, you can assume it's balanced, but let's be sure. 2 sulfur, 2 sulfur, 6 oxygen, 6 oxygen. So that one's balanced. Now we can go to the question. How many moles of sulfur trioxide can be produced from 7.2 grams of oxygen and excess sulfur? So we're told that's excess. And this would be the limiting. At what? 7.2 grams. And we want to find out how many moles of this. Okay? Remember, there are great walls in this equation. There's a wall here and there's a wall there. You can't get over, you can't get under that wall unless you've got moles. We don't have moles. We've got to find moles of oxygen. So how do you do that? 7.2 grams of O2. It's a conversion problem. We need some factor that will give us moles of O2. Right? Grams in the numerator, grams in the denominator, so that they will cancel. Moles in the answer, moles in the numerator. Grams per mole. Molar mass is what we're looking at. So what's the molar mass of O2? Well, each oxygen is 16. grams per mole. But we've got 2 of them per molecule, right? So that's equal to 32 grams per mole. Now this is, let me write that in here. This says grams per mole. So grams, in this case, goes on the bottom per mole. Now we divide 32 into 7.2. And we get 2.2. I'm going to keep an extra significant figure. And the reason I do that is to avoid rounding error. If I round it here and then I do another calculation with it, I could end up with a significant error in the final answer. So I'm going to keep that one until the very end. So this is how many moles of oxygen. Now how many moles of sulfur trioxide? Well, 2.25 times 10 to the minus 1 mole of oxygen converted to moles of SO3. So moles of SO3 would be on top, and oxygen would be on the bottom, right? Moles over moles. The ratio there, the conversion factor, is from the coefficients. So 3 oxygen and 2 SO3. So I multiply that value times 2 and divide by 3. And I get, now I can round it. 1.5 to 2 places, right? 2 places, times 10 to the minus 1 mole. Or let's see what the answers. The answers are in standard notation. So 10 to the minus 1 moves this decimal to the left. 0.15 moles. Okay, that's B. Okay, 82. 82. Consider the following unbalanced equation. How many moles of water are needed to react with 206 grams of aluminum carbide? All right. First thing you have to do is balance the equation before you can answer a stoichiometry question. So we've got aluminum carbide plus water yields what? Aluminum hydroxide and methane. Okay. Now we can use the budget method. Let's do that just for practice. So we set up our budget. We have aluminum, we have carbon, we have hydrogen, and we have oxygen. So now we do our first inventory. 4 aluminums, 3 carbons, 2 hydrogens, and 1 oxygen. And on the product side, we have 1 aluminum, 1 carbon, hydrogens. We have 3 here and 4 there. That's 7. 7 hydrogens. And then oxygens, we have 3. Okay. Now, remember our tricks or yeah, let's just call them tricks. We don't have any standalone elements here, so we can't hold those to the end. We generally hold the water to the end if we can. But in this case, where do we start? Well, one place is as good as another. Let's just start with aluminum, right? Start with aluminum. We need 4 on this side. Right, so that's 4 aluminums. Now that changes the oxygens. 3 times 4 is 12. Okay? And the hydrogens. 3 times 4 is 12 hydrogens, plus 4 is 16. So we have 16 hydrogens. Okay? Now let's go to carbon. We need 3 carbon. So we put a 3 here, and that gives us 3 carbons. Now we changed our hydrogens again. So 3 times 4 is 12, and 3 times 4 is 12. We have 24 hydrogens. Okay. Now, if we need 24 hydrogens over here, the coefficient should be 12, correct? Right. That would be 24 hydrogens. That also changes the number of oxygens. And we're balanced. Okay. So now if the equation is balanced, we can move ahead with answering the rest of the question. All right. So we're given, let's see, 206 grams of aluminum carbide. 206 grams of aluminum carbide. And the question is, how many moles of water are needed? So we're looking at moles of water to satisfy that equation, right? Remember, you can't move anywhere unless you've got moles. So this has to be converted to moles. We need the molar mass for aluminum carbide. Right, so that's 4 times what's aluminum? 2698.98 grams per mole. And 3 carbons, 12.01. Okay, so let's add those up. All right, and then 12.01 and 3 times, add those together. So I get 143.95 grams per mole. Now we can convert that grams of aluminum carbide to moles of aluminum carbide. We need grams on the bottom and moles on the top. So grams goes on the bottom, 143.95. There we go. We're going to divide that into 206. And I get 1.431 moles of aluminum carbide. Okay, now we convert that to water. The ratio then is going to be aluminum carbide and water on the top. So the ratio is 12:1, right? There's a 12 and there's an understood 1, always, right? We don't write the 1, it's there. All right, what's 12 times that value? And I get 17.1726 moles of water. Now let's round it correctly. Right? We had 206. That's 3 significant figures. So we're moving to that position. 17.2. 17.2 moles. Which would be B. Okay? All righty. see. Okay, scroll to the next one. 84. Consider the following reaction where X represents an unknown element. Okay, so we're going to be working with this equation. 6X solid plus 2 diborane 2B2O3. 2B2O3. Actually, it's diboron trioxide. And yields tetraboron X tri-X solid, let's see, solid, and XO2 gas. Okay. Let's see if I wrote that correctly. 1, 2, 1, and 3. Good to double check. Okay. If 165 grams of X, okay, reacts completely with diboron trioxide to produce 2.29 moles of B4X3. 2.29 moles. What's the identity of X? Now this reacts with that to produce this, right? So those are not in the reaction together. This starts off with some of this, right? Some of that, and produces this. And we want to know the identity of X. So how do we tell? How do we find out the identity of an element? There are only 2 ways. One way, well, actually there are a bunch of ways, but instrumentally speaking, there are a lot of ways. But for our purposes, with this information, we only have 2 choices. You can either find it on the periodic table by the atomic number if you have that. We don't have that. The only other option is molar mass. What's the molar mass of each element? Most of them are significantly different from each other. So if you find the molar mass, you can usually find the element. There are only a couple places in the periodic table where they're so close together that experimental error could overlap them, and then you'd need a tiebreaker. But for our purposes, I think we can go with molar mass, and I abbreviate that MW for molecular weight. And we need the mass divided by the moles. Do we have the mass? Yeah, we have the mass, 165 grams. What we need is the number of moles that mass represents. Okay? So, if we know this many moles and we know the ratios. So if we say 2.29 moles of B4X3, and we want to convert that to moles of X. What's the conversion factor? Well, B4X3 is 1 coefficient, and X is 6 coefficient. Right? So 6 times 2.29 is 13.74 moles of X. Now we have moles. 13.74. We divide that into 165. And I get 12.009 grams per mole. Now we go to the periodic table. We look at the periodic table and we just follow it from upper right, upper left, hydrogen, right, helium, and then we just keep going backwards, straight across the periods and down, skip down period, until we find the closest one to 12.009. And if you do that, you'll find that this one is carbon. So we reacted carbon with diboron trioxide to produce B4C3 and CO2 gas. Okay. Right. Next. 88. Consider this reaction. Magnesium silicide plus 4 water yields magnesium hydroxide and silane. That's the name for SiH4. How many moles of excess reactant are left over if we start with 39.1 grams of each reactant? Okay, so let's write our equation up here. That's correct. Yes. For water. Produces magnesium hydroxide aqueous. Go. And silane. 4. The reason that one is called silane because in the carbon group, carbon with 4 hydrogens is methane. And just below carbon is silicon. So silicon is going to have a similar reactivity with hydrogen and give you SiH4, right? They behave the same way. They're in the same family, same group. So instead of saying methane, we just substitute silicon in there. Silicon, A-N-E. So that's silane. All right, let's get back to the problem. If we have 39.1 grams of each reactant, what does that mean? That means one of them is limiting. How many moles of excess reactant are left over? So once we find out which one is limiting, all of that one is used up. But there will be some left over for the excess. In order to determine which one is excess and which one is limiting, we have to know moles. There's no way around it. So we've got to convert this one to moles. Right? We need grams here, moles there. That means molar mass. So what's the molar mass of magnesium silicide? Let's see, 2 times magnesium, which is 2431. Excuse me. Yeah, 24.31. And then 1 silicon, which is 2809. Okay. So 21.31 2 times and then 28.9. This is 76.71. So let's divide that into 39.1. And we get 0.5097 moles of this compound. Okay. Now let's do the same thing for water. grams per mole. I have that one memorized, but here's how you do it. 2 times hydrogen and 1 times oxygen. And that's 18.02 grams per mole. Divide that into 39.1. And I get 2.1698 moles of water. Okay. All right. So which one's limiting? Well, let's see. For every one of these, you need 4 of those. All right. So if we convert this one to moles of water, that'll tell us if we have enough water. How about that? All right, 4 there and 1 there. So 4 times that value is 2.039 moles of water are required for that much magnesium silicide. Do we have enough? Yeah, we got plenty of water. We got excess water, 2.1698, and we only need 2.039. So that means this one is limiting. And this one, water, is excess. Okay, so all of this one's going to be used up, and it's going to be converted using up that much water. So how much water is left over? You just subtract 2.039. Let's do 8. Okay. 0, 1, 3, 1. And we can keep, let's see, we had 3 significant figures. We can keep, well, actually, we can only keep 2 of those because 3 significant figures here and 3 there would only give us 2 here. So this is actually 0.13 moles of water excess. Okay. That's the answer. D. $92. Yeah. Okay. Fe3O4 reacts with carbon monoxide according to the equation as given. It's missing a plus sign in this one also. If 482.3 grams of carbon monoxide is reacted with excess, what mass of CO2 will be produced? Okay. So this one is fairly straightforward. Fe3O4 solid plus carbon monoxide yields carbon dioxide go. Yes, and 3 iron. Okay. All right. Let's see, as long as I've got written correctly. Yep. So 482.3 grams of carbon monoxide. Okay, and excess. Fe3O4. We want to know mass of carbon dioxide. So how many grams? Okay. Now we have to convert to moles, don't we? So 482.3 grams of carbon monoxide. We need to know the molar mass. All right, carbon is 12.01. Oxygen is 16. 28.01 grams per mole, divided into 482.3 is 17.2189 moles of carbon monoxide. So we're going to convert that to carbon dioxide. Well, look, for these, for those, it's 1-to-1. So you've got the same number of moles of carbon dioxide produced. Now we can convert that to grams. This time, moles on the bottom, grams on the top. So in order to calculate the molar mass for carbon dioxide, we actually need 2. 16 times 2 oxygens. 44.01. Right? So 44.01 times that value is 757.80. 0.802 grams. Now let's see. We have 4 significant figures, so we're rounding it to that position. 757.8 grams. Okay, and your answer is C. All right, scroll just a tiny bit and we'll get 94. (0.216 gram sample of sodium chloride. And they give you the molar mass there. Isn't that nice? Dissolved in enough water to make 5.20 milliliters of solution. Calculate the molarity. All right, let's work backwards. What is molarity? It's an expression of concentration, right? It's an intensive property, and it's a ratio. Molarity is a ratio of number of moles of solute per volume in liters of solution. Okay, so we need to make sure we have the right units of measure. 0.216 grams of sodium chloride is not molar, is not moles. We have to convert that. Right? 0.216 grams of sodium chloride. We're going to convert it to moles. Grams on the bottom, moles on the top. Right? And we're given the value there, 58.44 grams per mole. So we'll divide that into 2.216. and I get 3.696 times 10 to the minus 3 moles. Okay, so that can go right here. 3.696 times 10 to the minus 3 moles. And what's the volume? This has to be the volume of the solution. And we are given that, but we're not given that in liters. We're given that in milliliters. 5.20 milliliters. How many liters is that? Well, if you do enough of these, you know that you need to move the decimal 3 places to the left. But if you don't remember that, just use your conversion factor. 1,000 milliliters for every liter. Right? And that will give you 0.00520 liters. Okay? So we put that up here. Now I can divide that in 0.00520. And I get, let's see, in standard notation, 0.71079 molar. But we're limited to 3 significant figures. Right? Because this is 3 significant, that's 3 significant. So I've got to chop it off right there. 0.711 molar. There you go. That's the concentration of this sodium chloride solution. All right, 95. Let's see, I think I need some renovation here. Okay. $95. For the titration of sulfuric acid with sodium hydroxide, how many moles of sodium hydroxide would be required to react with 1.5 liters, 0.5 molar sulfuric acid to reach the endpoint? All right. There are 2 approaches to this one. Probably the easiest one, the more secure one, is to build the equation for the reaction and then work it as a stoichiometry problem. So if we're titrating sulfuric acid, with sodium hydroxide, what are the products of every acid-base reaction? Salt, sodium, sulfate. That's a 2 minus, this is a 1 plus, we need a 2 right there in aqueous solution, and water. Okay? So let's balance this equation. We need 2 sodiums over here, right? 2 sodiums. And that gives us 1 sulfate here. We can keep that together. That's intact. What we're looking at is this hydrogen. 2 hydrogens and 2 hydroxyls equals what? 2 waters. There you go. Now we're balanced. Okay. So now we can look at the problem as a stoichiometry problem. 1.5 liters of 0.5 molar sulfuric acid. 1.5 liters of 0.5 molar. And the question is, let's see, how many moles of sodium hydroxide? Okay. So how do you get moles out of that? Well, remember the definition of molarity equals moles per unit volume. If we want to know moles, solve for moles, we have molarity times volume. Molarity times volume. All right, so that's 0.75 moles of sulfuric acid. All right. Now we can convert that to moles of sodium hydroxide. We just need the coefficients. 2 there, 1 here. All right, so that's 1.50 moles of sodium hydroxide. All right. Yeah, I think that's the best way to solve it. For this course, there are other approaches, but this one is foolproof. All right, 96. Which of the following statements is false? All right. Oxidation and reduction. All right, let's look at each one. Let's see, are they all unique? Yeah, every answer is unique, which means for test-taking technique, if every answer is unique, then you work your way down until you find the right answer and you stop. How about A, cannot occur independently of each other? We're looking for the false one. This one is true. Oxidation always accompanies reduction. No exceptions. B, accompanies all chemical changes. Nope. All we need is one example of a reaction that's not oxidation reduction, and that makes B false. Right? Can we think of one? Well, let me see. How about the reaction we just had? Right? Sodium hydroxide plus sulfuric acid makes sodium sulfate plus water. That's not a redox reaction. That's an acid-base reaction. Right? Some acid-base reactions are redox, but not that one. Sodium didn't change its oxidation state. Sulfur didn't change it. Hydrogen didn't change its oxidation state. And none of them did. So that acid-base reaction is the only one we need to prove that B is false. And that's our answer. So C, D, and E should be true. Oxidation reduction describes the loss and gain of electrons respectively. Oil rig, oxidation is loss, reduction is gain. So C is true. D, result in a change in the oxidation states of the elements involved. Absolutely. Every time. And E, always happens when an alkali metal and a halogen react. An alkali metal, let's take an example. An alkali metal, sodium, reacts with a halogen. That makes sodium chloride. Right? 2 here, 2 there. Remember, these are 0 oxidation state. This is a +1, that's a -1. That's true. Happens every time. Whenever you have an element ends up in a compound, you have an oxidation reduction reaction. So that one's also true. We just confirmed, right? We found our answer, but I was interested in confirming the rest as true. 97. Let's see, you have 3 liters of 3 molar solution of sodium chloride. That's solution A. You also have 2 liters of 1.84 molar solution of silver nitrate called solution B. Mix these solutions together and make solution C. What's the concentration of nitrate ions in solution C? All right, what happens when we mix these two together? Sodium chloride in solution. And we mix it with a solution that has silver nitrate. Okay? What happens? You get a double replacement or an exchange reaction. Silver goes to chloride, sodium goes to nitrate. And if you look that up in your useful information, the chart, the solubility chart, you'll find that this one is not soluble, makes a solid. That's what drives the reaction, actually. And what's left over? Well, you have, let's see, sodium and nitrate, which we determined is soluble. What does that mean? That means we started off with those ions in solution. These separate ions in solution. This makes a solid. These ions are still in solution. So what does that make them? That means they're spectators. They don't participate in the reaction. The reaction is actually between silver and chlorine. So if we start off with a certain amount of nitrate on this side, we're going to end up with exactly the same amount on that side, moles of. Right. So solution A has 3 liters of 3 molar. 3 liters of 3 molar. And solution B is 2 liters of 1.84 molar. 2 liters, 1.84 molar. So if we need to find out the concentration of nitrate in the final reaction, in the solution, we need to know the number of moles of nitrate. Okay. So this gives us what? Let's see, 3.68 moles of silver, silver nitrate. And since that's in solution and the ratio is 1:1, we also have 3.68 moles of nitrate. Okay. Now, what's the concentration? Well, we need the final volume. What's the final volume? Well, we put 3 liters of this together with 2 liters of that, right? So it's 3 plus 2, or 5 liters. So 3.68 divided by 5 is 0.7, let's see, 3 significant figures, 3.6 molar nitrate. Okay, that's how you get that answer. Which of the statements is true for the following reaction? All right. So let's erase and make room. '99. So we have this reaction. We have 2 potassium plus copper 2 chloride yields what? Potassium chloride plus copper. All right. Now, we know that this is an oxidation reduction reaction because that element ends up in this compound. And this copper in compound ends up as an element. Right? So we know what's happening here. The question is, which one's reduced and which one's oxidized? Well, if we draw our tie line from this potassium to that potassium, what happened to it? In order to go positive, we had a loss of 1 electron for every potassium. But there are 2 potassiums, so we had 2 electrons lost. Okay? This copper, nothing happened to the chloride. Chloride's -1, both of them. This copper went from here to here. So how did it go from a 2+ to a 0? It had to gain 2 electrons for each copper times 1 equals 2 electrons. Gain. Okay, now we can say something. Look at the answers. Oxidized, reduced. So which one was oxidized? This one. Oxidized. Oxidation is loss. Reduction is gain. Okay? So let's see. Potassium is oxidized, A. Is that right? Yeah, A is true. How about B? Potassium, well, it can't be both. It's either oxidized or it's reduced. So B is false. How about C? Copper is reduced. Yep. Copper in the compound is reduced. So C is true. That means 2 of the above are true. That means E is true. There you go. There's your answer. All right, 102. In which of the following does nitrogen have an oxidation state of +5? All right. So let's see. A, B, C, D, E. Let's see. A is HNO3, NO2, N2O, NH4Cl, and NaNO2. Okay. We're looking for oxidation state of +5. So how do we find that? Well, oxygen is assumed to be a -2. And hydrogen in this case is a +1. So 2 times 3 is a -6, and a +1 equals a -5. That means this nitrogen must be +5 to balance the charge. This is a neutral compound that has to be balanced by this value. So there's your answer. While we're here, let's just do the rest of it. All right, so -2 means -4. That means this is a +4. -2 is balanced by a +2, but there are 2 of them, so that one's only a +1. This is a -1. This is +1, which is +4. So +4 -1 is a +3. We need a -3 for the nitrogen. There. This is a +1. This is a -2, -4 total. +1 means -3. This is a +3. Okay. So there are all your oxidation states. +5, +4, +1, +2, +3. Nitrogen has lots of possibilities. Just like, well, carbon does too. Let's do 103. Now, the reason I did all of those is because suppose I change parameters. I just use that same question in the test, and I say, instead of +5, I say +3. You got to be able to find the +3. It's not going to be A anymore. It's going to be one of the others. Okay, 103. Which of the following is true for a galvanic cell based on the following reaction? All right. So this is the overall reaction for our galvanic cell, our battery. Is it in that order? Yeah. And copper. There we go. So, reduction, oxidation, cathode, anode. Okay. So we're going to do that, and then figure out which one goes where. Right? Zinc goes here by what? Loss 2 electrons per zinc. That's how it goes from 0 to positive. Times 1 equals 2 electrons. Okay, that means copper gained 2 electrons for every copper. Times 1 equals 2 electrons. Okay, which one is oxidized? Zinc is oxidized, and copper is reduced. Okay, so which one's the anode and which one's the cathode? Remember, by definition, the cathode is the site of reduction. So this is the cathode. This solution with that electrode in it. Copper. Right? That will be the cathode. That means the anode would be this one. With zinc 2 plus, right? And we have a salt bridge. And then we'll connect these with a meter. Okay? That means the electrons are flowing that direction. From the anode to the cathode. All right, now let's answer the question. Zinc is being reduced. No, zinc is oxidized. Zinc serves as the cathode. No, zinc is the anode. Copper 2 plus ion is being reduced. Copper 2 plus, yes. C is true. Okay. D, copper serves as the anode. Nope, serves as the cathode. That means that's the only true statement of those 4. And E can't be true because only one of them is. Okay. 103. All right. Scroll 105. Total mass of a solution is 184.8 grams. The solvent mass is 125.2. What's the mass percent of the solute? All right. Total mass, 184.8 grams. Okay, that's the total mass. What's the mass of the solute? The solvent is 125.2 grams. So the solute would be the difference. Times 100. There you go. Like I said before, that's the thinking part. The rest is number crunching. Let's see, 125.2. So let's see. And let's see. It's going to have 3 significant figures out of this one right here. So we can go to 32.3%. Okay. Now, why did I say three significant figures? This is the significant figure rule for add subtract. And if you put 184.8 minus 125.2, right? Line up your decimals. We can keep that one. We can keep this one, right? And 2 from 7 is 5. We can keep that one. And that's 0. So the answer only has 3 significant figures. And when we put that in this part of it, 3 divided by 4, the least one is the determining one. So only 3 significant figures in your answer are possible. All righty, 106. Time. Okay, we're good. Electrolysis. What is electrolysis? Electrolysis is a spontaneous oxidation reduction reaction, which is forced to go in reverse in the non-spontaneous direction. That's electrolysis. Let's see, which one of these fits? A, B, C, D, or E? All right, A says, electrolysis is a process where electrical energy is used to produce a chemical change. Yes, we're running the reaction in reverse. So the electrical energy is forcing the reaction to go in reverse. Yeah, that's true. How about B? Electrolysis involves forcing a current through a cell to produce a change that would otherwise not occur. That's also true. That's another way of saying A. C. The electrolysis of water produces hydrogen gas and oxygen gas. That is absolutely true. Right? And if we balance that equation, we need 2 there and 2 there. That is true. How about D? Electrolysis is used to recharge a lead storage battery. It's absolutely. Right? The spontaneous direction converts lead from one electrode and lead oxide from the other electrode into lead sulfate, both of them. And when they do that, that spontaneous reaction produces a current that can drive your accessories in the car or start the motor, run the starter. In order to put energy back in, we have to take the alternator and convert, rectify the alternating current from the alternator into direct current and run it through your battery in reverse to drive the reaction backwards. And take the lead sulfate and make lead oxide and lead for the 2 electrodes. So yes, that one is also true. So that means all of the statements are true. Yep, every one of them. 107. Oxidation state of chlorine in the chlorate ion. Chlorate polyatomic ion. So remember, the total of the oxidation states has to be the charge on the ion. So we're given oxygen as -2. Right? -2 times 3 is -6. But we got to hold one of them out for that negative. So we really only have to balance of -5. That means a +5 here will lead to a net -1. Right? So the answer there is E. (108). Yep. We're going to do another one. Looks like we've got several coming. Oxidation state of oxygen. Okay. This is kind of a trick question. An element in its most stable state at room temperature and pressure is always oxidation state 0. Okay. There you go. That's C. $109. Sulfur in potassium sulfate. So you got two possibilities here. You take the whole compound. You know that potassium is an alkali metal with a +1. That means +2 total. Oxygen is a -2 with -8 total. So combined, that's a -6. That means sulfur has to be a +6. Or if you have sulfate in some other compound, it doesn't matter which, take the sulfate out. You know that sulfate is a 2- polyatomic ion. That means oxygen is -2, -8 here. Keep two of them out. So we only have to balance a -6 with a +6. Both ways work. $109, $110. When the following reaction is balanced in acidic solution, okay, the coefficient of water is. All right, so this is 110. And we're starting with ClO3 minus, ClO3 minus, and Fe2 plus, Fe2 plus. And we have chlorine, chloride ion, plus Fe3 plus, correct? Yep. Okay. To balance this equation in acidic solution, we need to use the oxidation reduction, the half reaction method. So we got to find out which one is the oxidation step, which one is the oxidation reaction, and which one is the reduction reaction. Okay. So we just did the chlorine, right? Let's do it again. -2, -5, +5. +5 for that chlorine, +2, -1, +3. Now, how about the chlorine? It went from +5 to -1. That means we had to add, it had to gain how many electrons? Well, to go to 0, it had to gain 5. But then to go one more, it had to gain another one, 6. So 6 electrons went from there to there. That's the reduction step. Okay, I'm going to put those in here now, since we only have one chlorine. 6 electrons, just so I don't forget. And the rest, the other one is oxidation step. Right? We lost 1 electron for each iron. We got 1 iron, so we can go ahead and do the electrons. And lost 1 electron there. Now, how do we compensate for the oxygens? We do that with water. 3 oxygens, we need 3 waters. And now we've added 6 hydrogens on that side. We need 6 hydrogens on this side. Now, these half reactions are balanced. In order to combine them, we've got to make the electrons the same, right? Because electrons don't exist out by themselves. Not even in particle physics. They're always attached to something. They may be excess, but they're always attached to something. So in order to combine these equations, we need 6 electrons in this top one. Right? So that gives us 6 here, 6 there, and 6 there. Okay? Well, now that we can combine them, just to answer the question, right? We're trying to save time on an exam. What's the coefficient for water? 3. That's it. We've answered the question. This is acidic solution. We don't have to do any further changing. Now, if it had said basic solution, we would bring them all down and then neutralize the hydrogens and cancel waters. And then we'd have possibly a different answer. But since this is an acidic solution, we can stop here and say, yeah, the coefficient for water is 3. All right, 111. The Hall process for making aluminum involves. All right. The Hall process for making aluminum takes bauxite ore, which is aluminum oxide. Aluminum oxide. Right? Ground finely. And we combine it with another aluminum compound that lowers the melting point. Okay. This is a molten solution of aluminum oxide and let's see, AlF6, that compound. We're not putting it in solution. We're not putting it in aqueous solution. We're melting it. Right? So we're electrolyzing. The electrolysis of the molten solution of these two compounds is basically the Hall process. Now, I didn't tell you during the discussion, during the presentation of this material, but Hall went out to he was living with his parents. He went out to his parents' garage, and he had a burner, and he had his batteries, and he had his electrical converters and whatever he needed. And then he went out to his parents' garage and experimented, right? And likely made a huge mess. That's where it started anyway. But yeah, the answer to this is C. We're electrolyzing the molten mixture of these two. All right, 112. Okay. How many electrons are transferred in the balanced reaction? Okay, this is already balanced. We just have to track the electrons. So let's write that equation. 2, chlorates plus 12 hydrogens plus how many iodides? 10. Yields what? 5 iodines plus chlorine plus 6 water. Okay. So, in this type of reaction, you don't have to worry about the hydrogens or the oxygens normally. When it's just hydrogens and waters, we ignore those. What we're looking at is that oxidation state, that oxidation state, that oxidation state, and this one, which is +5. We determined that one earlier. All right. So if we're going from this chlorine to that chlorine, remember, we went from +5 to 0 in this case. So we gain 5 electrons per chlorine. And we have 2 chlorines, so we have 10 electrons. Now that should answer the question, but we want to be sure. So if we go from this one to this one, that means a loss of 5 electrons, right? Going from, actually, no. Loss of 1 electron. 1 electron from here to here. Times how many iodides? Times 10. 10 electrons. There you go. So it's confirmed. 10 electrons moved in this balanced equation. All right, 113. Basic solution. Okay. 113. So we're starting with MnO4 minus MnO minus Cn minus and MnO2 and CnO minus. Okay, we need the half reactions. So -2, -8 total, -7 to balance, +7. Right? Nitrogen, in this case, we have to assume that it's a -3. So we only have to balance -2. That's a +2 here. Okay. -2 times this, -4 +4. Okay. And -2 -3. So that's a total of -5, but we only have to balance -4 because we need that charge. So that's a +4 for carbon. All right, now we can say manganese went from +7 to +4. It had to gain 3 electrons. That means it's the reduction step. MnO4 minus goes to MnO2. Okay, the oxidation step then must be this one. Cn minus at +2 here to CnO minus at +4 there. Okay, so next we balance the non-oxygen, non-hydrogens. Manganese, manganese, we're good. Carbon, carbon, nitrogen, nitrogen, we're good. Now we're going to balance the oxygens. So we've got 1 oxygen over there. We're going to add 1 over here. And that means we need 2 hydrogens. Okay. We have 4 oxygens here and 2 there. So that means we need 2 more oxygens over here. That means 4 hydrogens on this side. Now we can do electrons. This one was an oxidation. That means we have electrons on the product side. We lost electrons. Actually, we lost 2 electrons. On this side, we gained electrons. How many? 1 manganese went from +7 to +4. We had to gain 3 electrons. Okay? All right. So now we need to reconcile the electrons. We have 3 here and 2 there. Cross multiply. So we use 3 here and we'll use 2 here. So 3 times 2 is 6, and then 3 here, and then 6 there, 3 here, 3 here, and 2 here, and 8 there, 6 there, 2 here, and 4 there. Okay. Now we can add together. Let's see if we can cancel any before we bring them down. Okay. The electrons are gone, right? They balanced. Hydrogens. We got 8 here and 6 there. So we'll get rid of those 6. That makes this 2. Okay. Waters. We got 3 waters here and 4 there. So we'll get rid of those 3, and that leaves us with 1 water. Now we'll bring them down. 2 MnO4 minus. Right. Then 3 Cn minus. Right. And then plus 2 hydrogens. On this side, we have 2 MnO2. And then we have 3 CnO minus. And then we have 1 water. Okay. That's acidic solution. Now we need to make it basic. So we're going to say plus 2 hydroxyls. And plus 2 hydroxyls. That makes this 2 water. Right? So 2 waters and 1 water. That means this one is 1 water and that one's gone. So the question is, what's the coefficient of OH minus? It's 2. Right here. There you go. All right. So this one requires that you can predict the products. Some reactions are predictable. In other words, if the reaction is described sufficiently for you, then if you know the reactants, you can predict the products. And this 115, the balanced equation for the double replacement reaction of lead-2 nitrate, potassium chromate. Double replacement. So we know what's going to happen with these reactants. What we have to do, though, is write the correct formulas. Right? That's why I made such a big deal of nomenclature in the beginning of the semester. You got to write these compounds correctly. Lead-2 nitrate. Lead, 2 plus, nitrate, 1 minus. That means we need 2 of these. And we're going to react that with potassium chromate. Potassium and chromate. There. Okay. So a double replacement reaction means, or an exchange reaction, means that these cations swap places. So potassium ends up with nitrate. Okay. All right. -1 plus 1, that's good. And then lead ends up with chromate. Right? 2 minus, 2 plus. Okay. Now we need to balance them. The nice thing about this type of reaction is, even though you've got polyatomic ions, they did not break apart. Right? So we could set up a budget. Right? We could like lead, nitrate, potassium, chromate, and balance them. But these double replacement reactions are usually very well behaved. Well, not always, but most of the time they are. So we have 1 lead, 1 lead. 2 nitrates. We need 2 nitrates. Right? Now we have 2 potassiums and 2 potassiums, 1 chromate, 1 chromate. That's balanced. That's it. All done. Now, one thing you'll notice here is I forgot to subscript these right here. That's my fault. Should be subscripted. 3, 2, 2, 4, subscripted. All right, there's your answer. Okay. Now, there are a host of others here that I could pick from. All on this page, they're all double replacement. So the trick to this one is to write the compounds correctly. Then do the swap. And they'll all be the same. Except for some of them might produce a solid. Right? For instance, here, silver chromate is a solid. Let's see, those are all double replacement. Let's see, what's on the next page? This is, looks like a redox reaction. Yeah. So write the balanced equation of aluminum oxide and carbon monoxide. Let's see, 124. Aluminum
oxide. This is a -2, this is +3. Fixed charges. This is a type 1 compound. 2, 3. Plus what? Carbon monoxide. This is a type 3 compound. 1 carbon monoxide, 1 oxygen. Yields what? Does it tell you? Yeah, aluminum metal and carbon dioxide. Aluminum metal and carbon dioxide. Did we do this one already? I think we did. Or did something like it. All right, so you can set up your budget, but with practice, right, we can do, well, let's not do that. We need to hold that one till last. Let's do the carbons. Carbon, carbon, that's good. 3 + 1 is 4 oxygens. We need 4 oxygens. Then we need 2 carbons. Oh, we better do the budget. I can see the problem. I can see a problem developing. So let's set up the budget. Aluminum, oxygen, carbon. 2 aluminums, 3, 4 oxygens, and 1 carbon. And 1 aluminum, 2 oxygens, and 1 carbon. Okay. Now, well, we're going to have to go to the oxygens. There's no way around it because we need to hold this aluminum out, right? That's one of our tricks. Single elements we hold till last because the coefficient in front of that one changes nothing but that one. So we're going to have to go to oxygens, right? We have 4 here. So what if we put 2 here? And that makes 4. Okay. But it also makes 2 carbons. Okay. So how do we get 2 carbons out of that? Well, if we put a 2 here and make 2 carbons, that makes 2 + 3 is 5 oxygens. Okay. So we're in a mess again. I'm thinking here. Let's start over again. 4, 1, 2, 1. Let's see if we can balance the oxygens. Right? Let's remove this 2. There we go. We have 4 here, but if we only mess with that one, how can we make this one? See, that's if you multiply any number times 2, you get an even number, right? So we want an even number on this side. How do you get an even number here? The smallest even number we can get here is to make 3 of those, right? 3 + 3 is 6. How'd you get 6 over here? Well, we multiplied by 3. 3 times that is 6. And 3 times that plus those 3 is 6. So that means 3 carbons, 6 oxygens. Now we have 6 on this side, and we have 3 carbons here. And then we need a 2 here for the aluminum. Okay, so that was a little tricky. The key was recognizing that we need to end up with an even number because any number you multiply times this one is going to be even. But you're starting off here with an odd and an odd. So how do you make these even? The simplest way is to visualize 2 times 3. 3's there already. Another 3 over here would be the 2. 2 times 3 would be 3 there. And that's how I got to the correct answer. It takes practice. I can't say it any other way. Some of them fall right into place, and some of them require a little extra brain power and experience. All right, okay, we're done.
All right. Now, those were sample problems in part one, last Tuesday, and part two today on Thursday. You need to know how to work each one of those problems independent, right? Don't just memorize the answers, because I could pick any one of these others out of this review document and I could change the parameters. So what you need to do is know how to work each one of the problems. Now, some of them where you have answers, just memorize answers, that's not an issue. But where you solve problems, I can change the parameters. And if you don't know how to solve the problem, then you're going to miss the question. So word to the wise, solve the problem, don't memorize answers. And we're done for today.